Okay, welcome back, everybody. This is part 2 of our search deep dive. So where we left off last time was we were in TransportSearchAction, if I recall correctly, where we had made it to the execute request method in TransportSearchAction. So of course we have this listener that I think I'm the one who renamed this to original listener. Just gonna confirm that. Oh yeah, yep, that's me. So anyway, so this is the listener that has an error that will respond back to the user, right? Because we're still running on the coordinator node here. But along the way, first off, as we construct a new listener, we do end up decorating the listener that responds back to the user. So this code here is starting at probably about line 458 going down. It's kind of backwards. So we say before we want to, before we respond to the user, we do want to transform responses if there's a search pipeline. So of course, search pipelines are this feature that was added in OpenSearch last year. Yeah, in 2023. That allow you to transform requests on the way in and transform search responses on the way out. And so this is saying, of course, this is called updated listener. Oh, okay, yes. Because of course, trace was added in. So yeah, we also have a listener where again, this goes backwards. So we have a listener for tracing. So this is the very last thing that runs before calling back the original listener. But then before that runs, we want to transform responses. But then before we can run the request, we end up going through this little sort of cascade where after we transform the request, we want to run this listener, and this listener, we construct a listener inside the listener. So before we actually run this, so after we transform the request, we go in here, which will construct a rewrite listener, which will then trigger the rewrite. So yeah, that's sort of the order, is that the search pipeline is given a chance to transform the request. Then the rewrite logic is able to kick in. And then the listener created by build rewrite listener executes. I don't think I want to go into the details of like, okay, how does a search pipeline transform a request? It's actually not very interesting. It's essentially just you've got these request processors and it iterates through them. And because they can be asynchronous, there's some messiness with chaining them together with listeners. So that part's not terribly exciting. Rewriting. Now you might be wondering like, okay, well, what is rewrite? So this is, you can kind of think of it as a very simple form of, in some cases, query optimization. In practice, it tends to be more related to, with the rewriting that happens at the coordinator level, it tends to be stuff that needs to incorporate some side information to kind of modify the query that we're going to run. So the way this works is the search source builder has a rewrite method. Let's take a quick look at that. So search source builder. So it implements this rewritable interface, which means that it implements this rewrite method, which takes a query rewrite context. Confusingly, so this is something that took me a while to figure out. Query rewrite happens both at the coordinator and at the shard level. So this query rewrite context maybe, so if it's just the top level query rewrite context, it's happening at the coordinator. But there's a subclass of query rewrite context called query shard context. So this is the one that kicks in at the shard level. And both of these get coupled. So we're still on the coordinator. So we call rewrite with the shard level query rewrite context. And then it iterates through, well, sorry, not iterates, but steps through all these different things within the search source that are eligible for rewriting. Now, it's worth noting, see, these are clearly synchronous calls, right? That we just say rewrite on the context. Well, some of the rewrites do some expensive things, like call out to another index. An example of that is, if we look at terms query builder, it has, so within its do rewrite. So there's, abstract query builder, the base class of all query builders implements rewrite, which delegates out to this do rewrite that subclasses can override. The default do rewrite does nothing. So in this case, there's what's called a terms lookup. Yeah. So this is, you can say, I want to do a terms query, but I don't want to actually pass in the terms myself. I want to go fetch those terms from another index. So I'm going to grab a document from another index that will contain the list of terms that I want to filter on. So fetching that document probably involves a network call, because it's probably calling out to another machine. At very least, it probably involves some disk IO. If the index is local, running the query could take a little while. So instead of doing a blocking call on the request thread, it says query rewrite context register async action, right? And so what that does is it asynchronously says, okay, well, I'm going to do this fetch to fetch from the terms lookup. We get the target index and doc ID. And so, that's how it fetches it. And then it calls back to whatever listener was passed in. So this is where rewrites, going all the way back to where we were. Yeah, it's worth noting that with the rewrite and fetch, this is why it needs to follow this listener pattern, is because some rewrites may involve a slow step that we want to execute and asynchronously process the response from that to chain these things together. So, but what we care about is actually what happens after the rewrite happens. This method called build rewrite listener, I apologize, I gave it that name because this code here was actually inlined within this execute request. So you can see how big this method is and how deeply nested it is in parts. Try to imagine sort of appearing in line kind of here. Yeah, the code was getting a bit convoluted. Calling this rewrite listener is not a great name, because it's naming the method based on what it executes after. Really, I would call this, if I were to call this something different now, which I suppose I always could, because it's a private method and we can rename it. A better name might be something like, I say, well, for some reason my Shift F6 didn't register, but a better method name would be like, I don't know, execute rewritten query listener. Yeah, maybe, but it doesn't actually execute, I guess. Build rewritten query listener. I don't know. It's naming stuff is hard. But if anyone has any suggestions, I'm all ears. So the point is, this listener will execute after the rewrite occurs. So if the source has been rewritten, then we update it on the search request. And this is where this whole thing has gotten very, very convoluted. I think this listener should probably be broken down. In particular, what bugs me a little bit is how things have just been kind of tacked on. So, point in time search was something added to OpenSearch in, I want to say 2021, I think. So, oh, no, oh, okay, yeah. So, yeah, the initial work for point in time search was, some of it was added before the fork and some of it was finished after. Right? So, okay, so yeah, this stuff with, so yes, the point in time stuff was started to be added. Both of these here are looking at remote cluster indices. So embedded within this is both the logic to search the current cluster, fan out to shards residing on data nodes within the current cluster, but then also one of the indices being searched, one or more, may actually be located on a remote cluster. And so if that's the case, we want to gather those up. And then we make a distinction. So yeah, this is a little bit confusing here. This set of remote cluster indices, actually really what it's doing is it's taking all the indices being queried and kind of groups them by which cluster they're on. And so what we're doing here is we're saying, well, actually, let me pull out the local ones, leaving the ones that are not local and therefore remote. So at this point on line 507 or 510, calling this remote cluster indices is misleading, but starting on line after line 516 is executed. Now they truly are the remote cluster indices because we've removed the local ones. Anyway, so I don't think I want to get into the details of cross-cluster search. It's not that exciting. Mostly it involves calling out to a node on the remote cluster and saying, hey, can you give me all the nodes over there that can handle the search request? And then it dispatches to those individual nodes as though they were local, but not always, right? So if you want to minimize round trips, right? Because fanning out to individual nodes on a remote cluster to say like, hey, I want to run the query phase. I want you to give me your top end doc IDs and their scores, and then I'm going to collate those with results from other shards, and then I'm going to come back to you. This involves multiple round trips out to those nodes. And so there's an option you can specify in your search request to minimize round trips. And that's where actually, yeah, the logic's arguably simpler if you're minimizing round trips, because essentially you're just taking the current search request, calling out to a node on the remote cluster and saying, here, you deal with this. And it basically runs the full search request on that cluster and sends back the complete search response. And yeah, that ends up getting collated with whatever we get from other remote clusters or the local cluster. As you can see, this else here is the logic specific to cross-cluster search. So as you can see, it's a bit long. Okay, it doesn't have that much branching, but I would seriously consider just kind of taking all of this down to, oh yeah, it's hard to find the balancing. Parenthesis, think this is it. And then I would say extract, and yeah, okay, cool. So this extracted thing, I'm going to rename it to, first I think I have to hit enter. Here. So I would say like do cross cluster. So this would be a nice little refactoring, I think. That, yeah, we just kind of split this out. Of course, yeah, we end up passing a fair bit of stuff, but yeah, let's get into execute local search. So we'll pretend that we're not doing a cross-cluster search. This is slightly silly, I think, that we have execute local search, which all it does is it just immediately calls execute search. But if I recall correctly, execute search is also used by the cross-cluster search. So yeah, that's why. And I guess the fact that we very clearly call something called execute local search makes it abundantly clear that this is local to the current cluster. Cool. So if you saw my indexing videos, there was a spot there where we abort the request if there's a cluster write block. Since we're through the search logic, we will abort the request if there's a cluster read block. So this is something you can do to, if the cluster is under excessive strain and you conclude that it's like, what, it's better to just flip the switch and disable searches and just wait for it to recover. That's an option. And this is where that reblock will kick in. Now, think about the fact that, for example, search pipelines and that rewrite logic happens before this. Like, maybe this should be moved a little bit earlier in the process, right? Because search pipelines and the rewrite logic can potentially be a little bit expensive. Yeah. So wouldn't be a terrible idea to move this a little bit earlier. So, what do we do here? Okay. This search context, I want to understand the distinction between these two, with the search context being null or not being null. All right, I need to stare at this for just a sec. Like, why? What's the difference here? Why would this sometimes be null and sometimes not? So if we come back to the execute local search, okay, so here we had a search context. We came from this thing with the rewrite listener. This search context. Yeah. Okay. Got it. Okay. So yes, in this case, the search context is referring to the shared search context of a point in time builder. So what happens when you create a point in time request, it'll go out to all of the shards, immediately open a Lucene reader, where a Lucene reader is immutable. When you create a Lucene reader, it points to the current Lucene index, and it continues to point to that version of the index. It increments the reference count for all of the current index files to make sure they don't get deleted. Like, changes can still be happening, but those index files that we're looking at will be preserved. And because Lucene files are write once, they will get modified, because files never get modified in Lucene. So so this search context, if it's not null, it means that we're doing a point in time search, which means that we have a reference that we're going to use on all of the shards to say, yeah, this is the precise point in time index reader that I want to use. So that as I send a series of requests, regardless of what updates have come in the interim, those requests will look at the same version of the index, the exact same index files. Okay, so getting back to where we were in execute local search, which was an execute search. So let's assume that we're not doing a point in time search, but and that's why, it has this little assert. It's like, well, the only way that the search context isn't null is if we're doing a point in time search. So throwing this little assertion here is a good double check. And this also explains why we have the get local shards iterator from point in time. Oh yeah, that's also a good point. Now that I think of it, of course, if you have replicas for your shards, those it means you have more than one copy of the same shard. Well, no two copies of a shard will necessarily be exactly the same. Well, sorry, that's not true with segment replication. With segment replication, where we actually copy scene files from one machine to another, then yes, you could actually have two shards with identical files. Well, and in general, that's the steady state with segment replication. In the classic document replication, where each shard, the primary and its replicas, are all doing the indexing themselves, a primary and a replica, if they flush at different points, they may have different sets of documents written out. On top of that, when you open an index reader, the ordering of segments isn't guaranteed to be consistent. So to guarantee with point in time search that you get consistent results, not only do you have to make sure that these index readers are helped on each of the shards, you also have to make sure to search the same copy of each shard, right? So if, say, you have two replicas and you created the point in time search to search the first replica, you have to make sure to go back to that same one. So I believe this is what this get local shards iterator from point in time is doing. But yeah, there's probably something, yeah, in the search context, yeah, we do have information for, well, in this entry set, right? We have for each shard, we have context related to the node. And so, yeah, I believe it's guaranteeing that, we will iterate through, well, yeah, a search shard iterator is actually saying it's an iterator that iterates through the copies of a shard. And so I'm pretty sure this is, yeah. So the fact that the target nodes is a singleton, it's guaranteeing that we go to the same target node for each shard. So, it's making sure that, yeah, our set of target nodes has size 1 and it's the one that was stored in the context. Cool. So I said that I didn't want to get into point in time search, but ended up sort of explaining it a little bit. So recall that I said this execute search method. So we went to execute local search, which called into this execute search. So we kind of left the cross cluster search path and kind of reconverted, right? So down here, right? So we're resolving the local indices. I believe somewhere in here, let me try to remember. Oh, no, that's it. I'm trying to remember if within this method, did we reconvert with the cross cluster search stuff? No, maybe not. Yeah. So the fact that this is explicitly saying resolve local indices and we get the local shard routing. And then from those local shard routings, we get the local shard iterators. Don't believe. Okay. Yeah. Okay. So at this point, if we get here, yes, we've potentially been called. Where do we have so we merge the set of shard iterators. Where did the remote shard iterator? Yes. There we go. So yeah, if we're doing a cross cluster search, we go off, figure out, do these cluster calls to say, okay, for all these remote indices, who are you going to call? And then that information is propagated into this execute search. Here's where we do the local shard resolution logic. So trying to decide how much I want to get into the shard resolution logic. It's It's a bit confusing. I actually just started to learn about the code last week, the week before, specifically because actually, if you're following along on my screen and following along on GitHub, the code on my screen is actually not the same as what's committed in GitHub right now, because right now I'm on a bring. But if you look down here in the lower right at my Git branch, it's called filter shards by slice. So this is actually a pending change that I have. I need to get the integration test passing. I hope they're passing now. I retried a test run last night before I went to bed, and hopefully it passed this time. Some unrelated test was failing. I added in this where if you do a sliced search, I was thinking like, hey, let's get the information about the sliced search, and we will pass that in to the shard routing logic. So when we try to get the shards that we want to search, it'll filter them based on the slice. Because historically what has been happening is, so with slicing, you can say, okay, I want to search this index, but I want you to slice the, I want you to, split the index into, say, 5 slices, regardless of how many shards there are. I want 5 slices, and I want to be able to, and I'm going to call those slices 0, 1, 2, 3, 4, right? And then what I can do is I can use 5 different clients. One client's going to search slice 0, one's going to search slice 1, another's going to search slice 2, etc. And this way you can parallelize your queries, split them across multiple threads. And what OpenSearch needs to do is guarantee that each slice represents a disjoint subset of the documents in the index. Well, the way that has been working is that we still fan out, like for each request on the slices, we fan out all the shards. But once the request lands on a shard, the slice resolution logic would kick in there and simply say like, oh, this slice doesn't match anything. And it would inject a match no docs query into the query. So it would still execute a query. It would still have this reader context that would kind of stay sticky on the shard, but it wouldn't match anything. And if you're doing slices with scrolls, so scrolls are like a point in time search, where as you go from request to request, you want to hit the same shard, you want to hit like the same shard running on the same node, and you want to keep the same Lucene index reader. Well, with that slicing logic, where we would fan out all the shards for every slice, let's say I have 5 slices and 10 shards, that's keeping 50 index readers open, or 50 scroll contexts. And by default, OpenSearch has a limit of, I think it's 500 scroll contexts. So, all that say, this is why, I recently, I have a pull request open to filter the set of shards that you're going to search based on a slice, right? Say you have 10 shards and you have 5 slices. Slice 0 would actually correspond to shard 0 and shard 5. Slice 1 would correspond to shard 1 and shard 6, etc. And so rather than fanning out all the shards, we can just filter them here at the coordinator level and dispatch the request just to the shards that are going to match. Yeah. And keep fewer search contexts open, so fewer Lucene index readers. Cool. So so this is where shard routing happens. If you're curious, this search shards method within operation routing sort of goes through, and we have various decisions that could be made based on, if you pass the preference parameter, you can specify the routing parameter, within a search request. You can, when you index documents, you could specify a routing string and say, oh yeah, I want this document to be routed not according to a hash of its doc ID, but a hash of this, whatever that string is. A good use for that is when you say, like, I'm indexing data on behalf of my clients, and each client has an account ID. And so I'm going to route the documents for each. I'm going to route them by account ID, which guarantees that all the documents for a given account will land on the same shard. And then at query time, if a particular client comes along, I can say, like, oh yeah, I know your account ID. Let me dispatch the request just to your shard, right? Because you know which shard has all the documents for that client. So yeah, that's custom routing option. Yeah, preference is, you could say, prefer local shards. You could say, I would prefer to hit the primary for each shard. Primaries can be slightly more up to date than replicas. And so maybe you would prefer to be guaranteed that you've got the latest version of each shard. Yeah. So, yeah. And of course, I added this logic down here to filter based on slices. So that's shard routing. Within the operation routing class. So as I said, that code is a lot more complex than you'd think. The logic for deciding which shards, which copies of a shard are eligible to be routed to. Yeah, there's a lot going on there. So from this, you get these local shard iterators where, as I said, for each shard, it'll basically be a list of copies of the shard that are eligible to be searched. Yeah. Oh, yes. Yeah, the per index alias filter. Yeah, I believe this is related to the fact that on an index alias, so you could say, here's an alias, doesn't really exist as an index, it's a name. But when I search this alias, I want to search this index or these indices. And in addition to searching them, I want to apply some filter to every query. Yeah. And so that's essentially what this build per index alias filter is going to do. It's going to kind of tack on those filters. Yeah. And then, okay. Oh, yeah. You can do per index boosts. So you can say, I want results from this index to have their scores boosted over some other index. So, oh yeah, this is, I don't know, I think slightly interesting that, so if we only have one shard, then you can force the search type to be query then fetch. They want to remember, which is interesting because that's the default. So historically, actually, there were, oh yeah, because I'm on main, the various deprecated search types have been removed here. So historically, there was one, oh yeah, you see number 3 used to be query and fetch. So I do find it slightly funny that, yeah, I guess there was the desire to clean up query and fetch and DFS query and fetch. So what they were doing, so the way a search runs on OpenSearch, we found out all the shards with the search request, with the query. Each of the shards will run the query, but not actually read, though. So Lucene will actually process the query, and it has a priority queue where it keeps the top end documents, typically by score, but essentially it's just keeping a document ID. So it knows where to go back and get the actual document from, but it's just a doc ID and a score. And so that we call that the query phase. So it's actually executing the query and saying, hey, this shard has, here are the top 10 documents from the shard, or it's the top whatever, based on the size that you specify in the search request. Those all get returned back to the coordinator. So, but it's not returning the full document source, right? Because the source for each document, the actual document itself, could be quite large. And like, yes, this is the top 10 from each shard, but the user has only asked for the top 10 across all shards, right? And so a lot of those documents would just get thrown away. And so what happens is the coordinator will just look at these doc IDs and scores, collate them, sort of say like, okay, I'm going to take the best of the best. I'm going to take the top 10 across all shards, remember which shard each doc ID came from. And then I'm going to go back and say, hey, shard number 3, I want this document, and this document from you. And that's it. And so that's the fetch phase. And so, yeah, this is where we have these multiple round trips between the coordinator and the target shards. It's very important to note that between the query phase and the fetch phase, the Lucene index reader is kept open. We're guaranteed to send the request back to the same copy of the same shard, because it has to hit the same Lucene index reader, because the doc IDs that we get back are specific to that Lucene index reader. So this can lead to some very funny situations where the query phase executes properly, and then before it's able to execute the fetch, the remote node dies, or the remote node gets overloaded. And so when you try to send the fetch, that fails. So that can lead to some funny things where, say, your total hits, like you return something back saying like, oh yeah, I matched 10 documents and here are the top documents, but you only send back, say, 8 because, you, from the query phase, you knew how many documents matched in total, but then the fetch phase failed on a shard. And so you weren't actually able to get the matching documents for that shard. All that to say, if there's only one shard, I suspect once upon a time, this may have said, if shard iterator.size equals 1, then set it to query and fetch. Gonna check. Yeah. See, so this became query then fetch in 2017. But yeah, when Simon removed the query and fetch search type. So he said it's been treated as an internal optimization for 2 major versions, but he's like, no, let's just get rid of it. Oh, he said, and fold the optimization in the case of a single shard into the search controller, such that every search with a single shard, non-DFS, will receive this optimization. Okay, so somewhere else, not here. So once upon a time, it was the case that, yeah, if there was only one shard, we would do a query and fetch, which means because there's only one shard, we don't need this collation step. We don't need to fan out all the shards, get the top N from every shard, send them back to the coordinator, and then find the best of the best, and then go back to the shards to do a fetch. If there's only one target shard, we could say, hey, give me your top 10 and just send them to, because I'm not going to merge them with anyone else's results. So yeah, rather than doing 2 round trips, we can do 1. Cool. But that code was moved somewhere else, and we'll probably see it later. So what else do we want to go through? Yeah, there's, special logic related to the requester, where I suspect, I think this also may have been one of these things that had, no, it didn't have it didn't have a query and fetch optimization. But yeah, so, okay, right. So I think we're almost free where we want to be for today. Yeah, we got through TransportSearchAction. So the next step, so this gets a little bit complicated. We get into the search async action provider. So let's take a look in here. So The search async action provider is an interface. In terms of implementations, I'm not a huge fan of this, honestly. The fact that the two implementations of this provider are essentially both anonymous classes. So the fact that this anonymous can be replaced with a lambda. So if I recall correctly, when I say replaced with lambda, oh yeah, that's an ugly lambda. Yeah, I don't like that. Anyway, yeah, I would probably see, like, if you look at the nesting here, right, where it's constructing a new anonymous abstract search async action, which then has these nested things. I believe these are related. When do we get to this execute request? Right. Okay. So yeah, this one is actually part of execute create pit or create point in time. So that's how we get to that version of constructing the async action. So we have an async action for creating a point in time. Again, I don't like the level of nesting. I don't like the fact that this execute request is only used in when you're creating point in time search. I think I would like to, sort of split this out into a separate method. I don't like the level of nesting that we have here. It's hard to follow. But in the meantime, let's look for the other implementation, which I believe was this one. Yeah. So when we do the do execute, we propagate down that, like, hey, this is when you're looking for a search async action, I want you to call this method. So yeah. So I mentioned that, yeah, we do a query phase, then a fetch phase. Well, there are other phases. If you're fanning out to more than 512 shards, so, then this pre-filter logic kicks in by default. So think that's the case. Is it only when you put more than 512? Oh, no. Sorry. 512 is when you do a DFS query, then fetch, where first it groups them into groups of 512. And we'll say, like, okay, search these 512 shards, then search these 512, then search these 512. Yeah, the pre-filtering, does that kick in all the time? It might. Yeah, okay, so, yeah, okay. So we delegate to another search async action phase where we disable the pre-filtering because, yeah, it's wrapped up in the pre-filter. Okay. So the pre-filtering, what that'll do is, say you're searching across an index alias. The index alias points to a bunch of indices. You're indexing logs, right? And you roll over your logs index every day. And then you have all the log indexes for the past month behind an alias, or for the past week. So when I search this alias, it'll fan out all these indices or indexes for the week. But say I have a filter as part of my search request, as part of my query, that says, I want search the results from Tuesday, right? And so it'll fan out all these indices, and a bunch of the indices won't have any logs from Tuesday. And so the can match phase is a very cheap preliminary, like, sort of, don't execute the query, but let me know if the query can potentially match. And so it'll first fan out all the shards. Every shard is essentially asked to return more or less true or false. It's a little bit more complicated than that, but hand wavy. It's kind of a shard predicate, right? And so all the shards where they say, oh no, they can't possibly match this query, they'll just return false. It'll be like, okay, well, thank you for your service. You were not involved in the search, and yeah, we send the request out to the remaining shards, the ones who return true. So that's the can match phase. If we're not doing can match, by default, normally we would execute, normally we're doing either the DFS query then fetch or the query then fetch. Recall I said DFS query then fetch usually kicks in once you have more than 512 shards. You can also explicitly ask for it. You can say in your request, you can specify a search type as a URL parameter and explicitly say, I want to do a DFS query then fetch. That's not necessary. Actually, no, sorry. The DFS query then fetch will actually, it will do some distributed statistics stuff. So it can be useful if you want to have more consistent scoring. Yeah, I guess that's a value to the DFS query then fetch. But I think we're going to leave it there. Next time, I'm going to go into the default search query then fetch async action. So this is for most searches, this is the one that's going to execute where, as I said, first it'll fan out to all the shards, execute the query, get back the top N from each shard, collate them, and then we'll go back and do a fetch phase. So yeah, let's see how that works next time. Thank you all for coming.
Thanks a lot, Michael.